do some more elements. I'm kind of jumping around the notes because I think, I just went straight off the notes in the last class, and I think that sometimes I like them and sometimes I don't. So let's try a couple elements here. Let's look at, we did lithium, right? It's 2 and 1. What if we do potassium?
19.
I know. So what's it got? 2, 8, 8, and 1. What about sodium? 2, and 8, and 1. Notice any similarities here? What's similar? They all end in uno. Eins. What if we did, what do you hear at the table? What if we do neon? Anybody? 2 and 8. What about argon? 2,
8.
Let's see similarities. Huh? These guys all end in 1, and these guys all end in 8. Why do you think they end with that number? You see any correlations anywhere?
They're gas and we're happy.
Those are noble gases. They're happy. Their outer shell is full, isn't it? Their part of that floor is full. We're happy. That's why noble gases are unreactive. Beyond that, what do you see? Where do you think that 8 helps you with anything on the periodic table? You think that 1 helps you see anything on the periodic table? Valence electrons. But hold on before we get to that term. Look at your periodic table. Lithium, potassium, sodium. Where are they at on the periodic table? They're metals. They're alkali metals. They are in group number 1. Neon and argon are noble gases. They're in group number
8.
That's cool. Don't y'all think that's cool? That's neat. Periodic tables arranged that way, huh? It's a handy tool. Y'all don't think so? Only chemists get excited about stuff like that. We'll look at nitrogen and phosphorus on the periodic table. What group are they?
5.
So when you do the electron arrangement, how many are you going to have on the last
5.
level? You better have 5. Okay? Does that make sense? And what's the special term we give to those electrons in that last level? They're called valence electrons. They're the electrons in the highest energy level. They're called valence electrons. Those valence electrons, as we'll see in chapter 6, we're going to skip chapter 5. We're going to do chapter 6 next. As we'll see in chapter 6, these valence electrons are the ones that cause problems. They're the ones that react. Okay? Because those apartment floors aren't full or they are totally full. If you're totally full like the noble gases, you're not going to do anything. But if your apartment floor isn't full, somehow you want to fill it up. Heck, you might boot everybody off that floor and just drop down one floor. Evict them. See ya. Or you might say, hey, I only got one room left over here. Why don't I put one more electron there? Okay. That's what we're going to see in chapter 6. Now, here's that evidence we were talking about. Those levels that we showed. Here's what happens. You have an electron hanging out in its energy level. here we have two different electrons. Okay? Doesn't matter which one we want to look at. Let's look at this one right here. I'll make him red. Here's an electron. I put that electron in a fire. What happens when you put your hand in fire? Burns, doesn't it? Gives you some what? Energy, doesn't it? Heat is energy, right? We just learned about that. So I put this electron, this element, in a flame, and it picks up energy. And the electron jumps up some floors. So here's my nucleus. Here's my electron. And I put it in the heat, and what happens? The electron comes way up here. Well, that electron can't stay there forever because that's not the lowest energy. It's kind of like when you have little, who has kids? You might have kids? Or little brothers, little sisters? Yeah? You been around little kids? Give them some candy. Give them some sugar. Give them a big old glass of Kool-Aid. What happens to them?
They get hyper.
They get hyper. That's that electron. It's hyper. It's all jacked up on sugar and Mountain Dew. I'm all jacked up on Mountain Dew. You got that reference? Some people got that reference. Talladega Nights. It's all jacked up. But it can't stay there. What happens to those kids after a little while?
They crash.
They crash. Big time. They get all grumpy, don't they? Because they got to come back inside, go back down to a lower energy level, don't they? So they go back down. So this is energy in. And when it comes back down, it has to give off energy. We can put energy in and heat, and this might be light that we can see. It might be visible. Y'all read that?
No.
Light, visible, maybe. That's close enough. Okay? So it's converted heat energy to light energy. And because these are discrete levels, right? We just agreed that these were discrete levels. This light might be a particular wavelength that you can see. It might be ultraviolet, it might be infrared, but some of the times it's visible light that you can see. And if we have some fancy pieces of equipment, we can measure the wavelength of that light, and we can say something about the energy of these things. And what we notice, it doesn't give off all these wavelengths of light. It only gives off certain energy levels that correspond to the difference between these energy levels. Okay? That's how we know that electrons exist at definite energy levels. They don't just have random energy. You give that kid sugar, it doesn't just go to some random energy level. It goes up to some high energy level and it crashes back down. It can't stop in between. Okay? So, and we already did this. We did those. I want you guys to practice writing these energy levels for a minute. I want you to write these four energy levels, these four energy diagrams for these elements. What's the first one? Carbon. How many electrons?
2.
How many
6.
total?
6.
6 electrons, right? So it's 2, 4. Done. Silicon. How many?
14.
2. Oxygen. 8 electrons. 2, 6. Nitrogen. 5. Notice anything for carbon and silicon? What group are they in?
4.
Group 4. Notice anything for oxygen? It better be in group 6. Nitrogen? Group 5. Okay? All these other electrons down here at lower energy levels, they don't do much. These are the ones that will be reacting, okay, when we get to that point. So, one of the things that we can do by using the periodic table and the group numbers and the electrons is look at some trends in the elements, start to understand something about the chemistry of these things. And we're going to use some of this information as we go forward. There are 4 things we can understand, or 3 things. Atomic size, ionization energy, and metallic character. And we'll discuss all 3 of them. So, we've already talked about this, right? Here's that term. Valence electrons. The number of electrons in the outermost energy level. So what we just did with those energy diagrams, the electrons are in the highest energy level are called valence electrons. They are the ones that will eventually react. And if you look at the periodic table, that number agrees with the group number. That's why, remember I said we had the numbering scheme 1 through 18 versus the 1A through 8A? And I said I like the 1A through 8A. Because I don't even, when I say group 7, I really mean 7A, right? That's the halogens, right? And when I say group 8, I really mean 8A. That's the noble gases. Okay? So, yeah. Easy enough. Now, one of the tools that we have is called a dot symbol. What a dot symbol is it takes the elemental symbol and it puts the valence electrons around it. Now here we have aluminum, sorry. And if you write the electron, diagram for aluminum is 283, right? It's in group 3, so it should have 3 valence electrons. Now we're going to only show the valence electrons on this diagram. So for aluminum, we draw aluminum, and then we put 3 dots. 1, 2, 3. Now my 3 dots weren't in the same place as their 3 dots. Who's right? Doesn't matter. The key is, do not pair the dots until you have to. Okay? So let's see. Let's do one with, so let's do sodium. How many valence electrons for sodium? 1. It's in group 1. So I could put that dot here, or I could put the dot here, or I could put it here, or I could put it here. Okay? Doesn't matter. Okay? Well, let's go to, let's do carbon in black. Carbon. 4 valence electrons because in group 4, right? 1, 2, 3, 4. Fair enough? What about nitrogen? How many does nitrogen have?
5.
1, 2, 3, 4, 5. Now, we're going to jump ahead. I'm going to tell you some stuff that's going to come in handy later on. When you look at these things, what do you see? I mean, to me, I see something up there with those dots. Does it just look like gibberish to you?
North, south,
North, south, east, and west where the dots are. Kind of looks like a compass. Well, look at nitrogen versus carbon. It has a pair on one side, doesn't it? What do you think that implies?
double the amount of.
Electrons like to be paired up. Okay? Electrons like to be paired up. So how many different things, so if I were to combine carbon with something else, let's say that hydrogen came in to combine with carbon. How many hydrogens do you think it would take to combine with carbon? It's going to take 4. Because hydrogen's going to bring 1 electron, and they're going to pair up. and this is methane. But for nitrogen, right, it only takes 3. So this is the formula for, do we know what that is? Most of you have it in your house. Anybody? Huh? Who said ammonia? Very good. It's ammonia, right? Notice it takes 4 hydrogens for carbon and only 3 for nitrogen because it wants to get some electrons to pair everybody up. And that's what we're going to talk about as we move forward in the semesters, how to do that. But this is the beginning of that, okay? Things reacting together and how many of each you get together, okay? We'll do a lot more of that in chapter 6.